Welcome to this tutorial on contour maps, drawing them and understanding them. We will also cover at the end geological maps and symbols. A contour is a line which joins all the data points of a certain value. In this case, we are looking at values of height or elevation. Each contour line is therefore perfectly horizontal, being a single elevation all the way along its length. Contours can of course be drawn for any kind of continuous variable, such as porosity, permeability, thickness, temperature, pressure, and so on. Contour shape and spacing tells us something about the gradient and slope of the data. On this topographic map, we can see that narrow-spaced contours indicate steep slopes, that widely spaced contours indicate gentle slopes, that contours have a V-shape in valleys and a rounded shape on hills. Closed contours indicate high or low areas on the map. All of this is useful for identifying topographic features like hills, valleys, cliffs, and so on when observing a topographic map. There are a number of key rules for drawing contour maps. The first are a set of golden rules for contouring which govern all contouring situations. Contours cannot cross and cannot merge. Contours pass between points higher and lower than their own value. If the gradient changes direction, then a contour must be repeated to indicate this change in slope. On maps, contour lines must close, connect to itself within the map, or end at the map's edge. In addition to these basic golden rules, we have developed a set of guidelines to help students contouring maps in the classroom. The first guideline is to use an even round number for the contour interval and make sure that you use at least 5 contour lines to adequately demonstrate the gradient of the data. In order to do this, it is best to start by examining the map and finding the highest and lowest points so that you can work out the right contour interval to use to get at least 5 contours. When you start contouring, always start with the data as densest or steepest. Always contour in pencil and always label your contours. Keep it simple. Use ticks or labels on highs and lows, and we will cover in this tutorial the art of placing contours between data points. Here I will demonstrate the various methods of placing contours between data points. To start with, we have 2 data points labelled 221 and 312 units, whatever the units are. We want to contour in 50 unit intervals, so we will need a 250 unit and a 300 unit contour in between these 2 points. To start with, we assume that the gradient of the data is constant between the 2 points. That means that if we were to place a contour every unit, there would be evenly spaced contours between the points. We can start by measuring the distance between the 2 points, and we know the difference in unit value. Taking these 2 numbers, we can work out what horizontal distance 1 unit would be, and therefore work out at what horizontal distance the 250 unit contour should be, and what horizontal distance the 300 unit contour should be, and mark these in. Then we can extend our contours from their current position between our 2 data points. However, this takes a lot of time, measuring and then drawing and so forth. It is often easier, and of course much quicker, to guesstimate where the contours should sit and then sketch them in. You will often find that in order to create smooth, realistic contours, we need to be a little loose about exactly where contours are located between data points. This is because our basic assumption of even gradient between points is actually incorrect. Slopes are usually not even between data points. Now that we have our method of contouring between data points, we can extend this to a map. We will assume that this map is of topography, so hills and valleys. In this case, we have evenly spaced data, so in order to start we need to look for the steepest gradient. We begin by identifying highs and lows on the map and marking these with a little label to help us see the shape of the data. Looking at the range of data, if we use a 50 metre contour interval, we should get 5 contours. The highest value is 484, so our first contour will be 450 metres. We can draw our 450 metre contour around our highest point. Our contour must either close or extend to the edge of the map. I have chosen the latter option here. But, oh no, I have made a mistake. This contour should enclose all the values higher than 450, and there is a value of 465 on the wrong side. This is why we contour in pencil, so that we can rub out the wrong bit and include our only other value higher than 450 within our contour of that value. We label our contour. You can put your label beside the contour line, but most professional maps have the labels in a break of the contour. Now we can move on to the next contour downslope, which will be the 400 metre contour. The 400 metre contour also occurs in this bottom corner of the map as well. We continue contouring until we have separated all the areas of higher and lower values with the appropriate contour lines, making sure that any reversals of slopes are indicated by repeating contours. Now the final contour in the top right goes in. The result indeed resembles hills and valleys as expected. Our next topic is what to do about faults. This map comes with some faults printed on, the thick black lines. We are now dealing with subsurface geology, so we are contouring the surface of a formation in the subsurface. Contour lines drawn on geological formations are also automatically horizontal and are therefore parallel to the strike of the formation. The shape of the contour therefore illustrates the shape of the formation, and these are therefore often called structure contours. Faults, of course, offset the surface of a geological formation so that contours will be disrupted by them as the offset across the fault changes the elevation of the surface being contoured. In this map, we can immediately identify higher and lower values. These are negative numbers, so they likely refer to elevation. Elevation is an absolute scale where the reference level or datum of mean sea level equals 0 units of elevation. You will see lots of text and discussion that use the words height and depth. These don't have a fixed datum but can be referencing a difference in elevation or the depth below, say, the land surface or the seafloor. In subsurface geology, we do often refer to our maps as being in depth, where we are using this to mean true vertical depth subsea, which does use a datum of sea level and is therefore equivalent to elevation. Back to our faulted anticline. I have already partially contoured some of the blocks between faults, but now I need to complete the contours which should go up to the fault lines and stop at the faults where the surface is displaced to another elevation. We should see a consistent displacement across any particular fault, although where faults join, the combined movement may see inconsistencies creep in. We can also tell how much movement has occurred across a fault plane by comparing the values of elevation of the surface across the fault. In this case, the surface has been displaced by about 20 metres vertically. We don't know how much horizontal displacement may have occurred, which complicates this calculation. So far, we have been talking about contour maps. However, maps can also be used to show discrete data like houses, rigs, pipelines, and geology. Geological maps are often made in colour, where each colour is a different formation or lithology. They can, however, be made with symbols or patterns indicating the different formations. This is more common where colour cannot or is difficult to use, which is older maps, diagrams, papers, and so on. Geologists tend to use a standard set of symbols that we learn from the beginning of our degrees. The brick pattern is always limestone, dots are sandstone, and so forth. We use a standard set of symbols for structures, like folds and faults, or to illustrate the orientation of rock units, so giving the strike and dip. I hope that this tutorial has helped you to understand how to contour and what to watch out for. Please see further details in the PowerPoint shows and other resources available on Vision, and do practice this new skill of contouring data.